So 4.6 we started yesterday, and we just talked about isosceles and equilateral. We're going to see some more of that, but we're going to throw in this idea of a right triangle. There's something unique about right triangles.
There's a lot unique about right
Yes.
triangles. We're going to do a whole chapter on right triangles
Yes.
later. You're going to learn more about right triangles than you ever thought you
I
would need to know before.
I know.
But we're going to just start with some really cool stuff for proving triangles can grow.
But let's do a quick super recap. We've done this before, but it's always good to do it again. Let's think of some ways that we can prove congruent triangles.
Okay.
So let's list them.
We, first of all, could use the kind of the definition of being congruent and say all 6 parts, but I'm thinking we're going to focus right now on the shortcuts because we don't really use all of the 6 parts ever. So we talked about side, side, side. So when 3 sides of one triangle are congruent to their corresponding sides of their other triangle, they're congruent. We talked about side, angle, side with that included angle idea. We talked about angle, side, angle with that included side idea. And we talked about angle, angle, side.
And really, that's it. I've heard the other day or a few days ago when we did this, I had some students say something about third angle theorem. That doesn't prove congruent triangles.
Right.
What about CPCTC?
That was after we already knew triangles were congruent. That allows us to talk about other parts of those triangles that are also going to be congruent. So really, these are the only 4.
This is the only 4. But I know I've been saying this in my class. There's actually one more way, and it's specific to a right triangle. Okay, so these 4 ways work for all triangles. They work for all triangles. The 5th and final way works for a right triangle. And you'll kind of notice the name of it when you see it, what that is. And it's called the hypotenuse-leg congruence theorem, and HL is for short.
Okay.
Okay, so notice the name. Hypotenuse involves
that side across from that right angle, that longest side. So it has to be a
right triangle. And a leg, we know legs are also involved in a right triangle as well. This is something we even talked about in section 1. All right, so the fact that it's called the hypotenuse-leg congruence theorem probably means it involves hypotenuse and leg, right?
Right.
Okay, so let's read it. It says, if a hypotenuse and a leg of a right triangle are congruent to the hypotenuse and the leg of another right triangle, then what does that mean? The 2 triangles are congruent.
Okay,
so kind of give you a visual. Look at this picture. First of all, notice these are right triangles, both of them.
So if they weren't right triangles, we couldn't definitely not use HL.
No, HL only works specifically for right triangles. So keep that in mind. When you already know the right triangles, you've established saying that basically right triangle means you have at least one right angle, or you have, one right angle. So if you've established that in your proof, or you can see that, then you know we can use this theorem. Okay? The other way you know you can use this theorem, and it doesn't work always just because it's a right triangle. It has to have certain things. You have to have the hypotenuses that are congruent. So in this case, notice the hypotenuses. These are these guys right here. And you have to be given some legs are congruent, which are
the AB and the CF. Now, could it have been the BD and the FE?
Are those legs?
Sure.
Yeah, so you actually have 2 legs to choose from.
So as long as it's a hypotenuse and one other side is essentially what this is, because either one of those are legs.
Yes. Now, the reason why this has to work for a right triangle, only be a right triangle, is because if you look at kind of just the relationship, the arrangement, if you think side, side, angle.
Oh, that's a bad word. We don't use that.
Side, side, angle doesn't work for all triangles. It only actually technically works with a right triangle, and we just don't use side, side, angle because of the fact that the angle is something unique. The angle has to be a right angle. Okay? So this is the case. So if you know, basically, the hypotenuse and the leg of right triangles are congruent. So if, let's say, AD is congruent to CE, these are your hypotenuses. I'm going to make a little note. And you know segment AB is congruent to segment CF. This is your leg idea. But you also have to know what? That these are
right
triangles. So basically, you have to be given right angles. So in other words, angle B and angle F are right.
Okay. And we have to know that they're right, not just perpendicular.
Exactly.
Because we have to know they're right triangles.
Right triangles. then you can say that the triangles
like ABD is congruent to triangle CFE. And my reason now is just going to be HL for hypotenuse leg.
Reason. So going back again, this slide right here, these work for all triangles. HL works for just specifically right triangles. So that's when you use it. Now, again, that doesn't mean HL will be used in proving every set of right.
Sure, because if I don't have a hypotenuse at all and I have those two legs, I would still have side angle side.
Yeah, so let's say, and what she's saying, let's say these sides were given congruent instead of the hypotenuses, then you could prove by side angle side. All right, so just to kind of keep in mind, we've done that actually before.
Yeah, this is just a way to get around. We obviously are not going to use side angle, so this is kind of the one exception to it, but we don't call it side angle because it's only with right triangles.
And the main reason, again, guys, is if you already know two sides of a right triangle, you can find that third side by using that Pythagorean theorem. So if the two sides of that right triangle happen to be the same in relationship to each other, those third sides are going to be the same.
Right, and that is really the proof of this theorem. All these theorems can be proven.
Okay, so let's try some examples with it.
Okay, so we're going to jump right into a proof.
Excellent.
Yes, and on this proof, notice they give us that D is the midpoint of CE. I'm going to go ahead and write that down.
And we've seen midpoint quite a bit. So that's going to be we know that's going to prove some congruent segments.
And we also have some perpendiculars. They tell us that BC is perpendicular to CD and that FE is perpendicular to DE. And we also know that BD is congruent to FD. So we've got lots of stuff here.
Yeah, so
in our given.
And the thing about the given is that they do give you I see already pair of congruent stuff, so I might go ahead and have you label that. So BD and FD are congruent. And I'm going to go ahead and take a look at that proof part. They're trying to get you to prove those two triangles are congruent. So there's not any other two triangles. They're not asking you to prove parts of those triangles are congruent.
So we're not going to be using
So it's really just let's get to proving the triangles are congruent and be done with it.
Right.
So let me start with the first part of the given. D is the midpoint of CE, so that's going to mean CD is congruent to segment DE, and that's because the definition of midpoint. We've used this a lot.
Yes.
So labeling that, I'm taking a look. Okay, if I want to prove two congruent triangles, I need... Okay, if I use any of the reasons we've learned up to today, I have to prove 3 pairs of congruent pieces.
So we've got really 2, and I'm going to mark these on here now too.
All right, let me look at the other part of the given just to see if it helps out. It says segment BC is perpendicular to CD, and segment FE is perpendicular to segment DE. Okay, I'm thinking, and I'm just going to share my thoughts out loud. If I have perpendicular segments, that means that I have some right angles.
Absolutely.
So I could say angle C is a right angle as well as angle E. And that's the definition of perpendicular.
Okay.
Now, the reason why I'm liking this idea so far is because what I'm seeing now is I have 2 triangles that are actually right triangles.
Uh-huh.
I see that their hypotenuses are congruent and a pair of their legs are congruent. Which means I could say these triangles are congruent.
We can, you're right.
And my reason would be HL, right?
It will be, you're right, because we've got we know that they're right triangles because we see that they've got right angles marked now. And they were given perpendicular, but we established that they were right angles. And that's important. They have to be right angles. So we have right triangles because we have those right angles, and the hypotenuse and the leg of one is congruent to the hypotenuse and the leg of the second one. So those triangles are congruent because of HL.
And HL, yes, and HL can be used because of the fact, again, that there are right triangles established here. What if I stated angle C and angle E are congruent because the right angle is congruence theorem? Would that be a bad thing?
Well,
or,
it's just not going to help you because then you'd be using side angle.
and we don't want to use
And that's
that.
not a reason and a proof that we can
So
use.
it's not necessary.
It's not a theorem.
So this is one where, guys, notice you only need to establish two congruent pieces, the hypotenuse and the legs, but you also need a third piece, and the third piece is that right angle thing about the right triangles. So you still need three pieces, just two congruent pieces and one right angle part.
Exactly.
All right. I think we have another proof coming up. Yep. So this one right here, I'm going to go ahead and start writing. And right away, notice they give you some perpendicular stuff, and we've already talked about what that kind of involves. All right. When you see perpendicular, what do we know right away?
We know that means we've got some right angles.
Okay. And which means we could maybe use HL as a reason to prove congruent triangles, but it may not always be the case. So let's look at it. It says segment MO is perpendicular to OP. So I'm going to go ahead and label that. We'll need to establish what that means.
Okay.
Segment RP is perpendicular to segment OP. So there's that. Segment MP is congruent to segment RO. So there's that. Anytime they kind of cross, just kind of be careful how you label it.
Right.
Something you might even do.
Just redraw it.
Yeah.
That's what I would think too. And I'm looking at the triangles they're trying to get us to prove congruent. And it's actually triangle MOP, so we could draw that one. And of that, we know we've got a right angle. Well, we know it's perpendicular, which we're going to say right angles here probably in a minute. And angle RPO.
So these two triangles, I kind of just separated them out. They gave you MO is perpendicular, segment OP, segment RP is perpendicular that. These segments are congruent as well. All right, so let's get going with it. Let's kind of go with what you were saying already, Ms. Hochgrabe. You said
when I know every time I see that perpendicular, I mean, unless I was trying to say maybe the two lines are parallel because they're perpendicular to the same line, the only other thing I'm probably going to use is the fact that they're right angles. And knowing what section we're in and that we're talking about right triangles, that's probably going to be a good idea.
Okay.
So I'm going to say that angle, and I can't just call it O,
Why not?
because as I look back at the original picture, I noticed there's lots of things coming off of O. So angle MOP is congruent, and angle, RPO are right angles.
And that's because?
Of the definition of perpendicular.
And I like that you said you can't say angle O. If I separate the triangles out, yeah.
It looks a little like it's just an O, but yeah, you got to always go back to that original picture when you're naming it. Now, I could talk about how those angles are congruent, but we learned today that may not be necessary. So I'm going to just keep going.
Just hold off on that.
I'm going to hold off on that thought. So, because right now I also have another set of sides that are congruent, and it's the hypotenuse of both of those. So I'm just going to see, looking at that, are there any legs that are congruent? And, I see OP is reflexive. It's on both of them.
Notice they're in the same, in both the triangles. And notice even in the original,
that's their overlap.
They overlap, they share that. So I could say segment OP is congruent to segment OP because of that reflexive. Well,
now I'm looking at it, and I've got a hypotenuse and a leg, and I've established that they're right triangles, so I've got my three parts. So I'm going to say that those triangles are congruent. Triangle MOP is congruent to triangle RPO, and that's another case of HL.
And we're using HL obviously more frequently. This is a very, very, very special theorem. It's not something we use a lot.
It only works for right triangles, and not even every case of right triangles, because you have to have it's not even given two angles. It's given the hypotenuse and a leg, and that's it.
But I like when this one you said, well, since they gave you the hypotenuses are congruent, that's a lot of times a red flag that this will be the theorem we might use. Not always, but a good suggestion of it.
Exactly. Okay. This next one, they tell us we've got several perpendiculars and some congruent statements. So I'm going to be writing this all out for a second. We say that BD is perpendicular to CD, and that GE is perpendicular to EF, And that we've got some congruent statements. CD is congruent to EF, and CB, I'm going to fit it in there, is congruent to GF.
You're just determined.
I'm determined.
This is a never-ending given.
It is, and I should have started smaller because I saw what was coming. I don't know why I started so big. And my reason, of course, is given. Now, I'm going to mark that. So I've got BD is perpendicular to CD. And I've also got that GE is perpendicular to EF. So I've got some perpendiculars in there.
Which usually means we have right angles.
It usually means we've got some right angles.
So
you're right.
maybe keeping that in the back of my mind.
And we also have some things that are congruent. We know that CD is congruent to EF, and that CB is congruent to GF.
Okay.
Well, Ms. Palermo,
are
what do
they
you
all
notice
congruent
here?
to each other?
Oh my goodness! I can't believe I just did that. Yes, they're not.
Okay, what were
Thank
you
you.
saying? Sorry.
What do you see? Just looking at what they've given us already.
Well, I'm thinking those two triangles, I can go ahead and say that they're congruent, right?
Close.
Close. What do I need?
Well, have we talked about? We've got our two congruent statements. What was the third thing that we needed to know?
Oh, yeah. Okay. We need to say we have some right triangles, so we got to establish right angles first.
You got it.
Okay, so because perpendicular, we're not assuming, we got to state it. So perpendicular means right angles. So angle BDC and angle GEF are right angles. And that's the definition of perpendicular.
Okay.
And the reason why I was thinking those two triangles are going to be congruent is because of the fact that I have the hypotenuses are congruent and the legs of a right triangle. So that means and that's because of HL. Okay, and again, I have two pairs of congruent pieces, the hypotenuse and legs, and I have right triangles.
And I noticed that you had to name those triangles again. They aren't giving you the triangle congruent statement in there, but keeping those corresponding pieces in that same order.
Okay, now,
Good.
I never really looked at the prove part. I just kind of assumed I'm proving congruent triangles. And it's not really assumption. I'm just feeding off what the given does.
Right.
And I think when you do these so often, you get comfortable with, okay, I know I got to use this for a reason. So now I need to stop back and kind of think, okay, a lot of times we are proving congruent triangles in these proofs, but we got to make sure we take it a little bit further sometimes. Like the proof says something about proving a triangle is an isosceles triangle. So I'm looking at the triangle that they're saying. That's triangle ACF. So that bigger triangle. So what the question you might ask yourself is, what do the two triangles that we just proved are congruent have to do with that larger triangle?
And what do you notice?
Well, they say they share some things, but I also want to think about, and something you mentioned yesterday. I remember you said it was great. When you're trying to prove isosceles, you're thinking of the definition. Isosceles means at least two congruent sides. So technically, I need to prove two of its sides are congruent. But the two that large triangle ACF doesn't have any sides comparable to the two smaller ones.
Right.
So I need to feed off what the two smaller ones have in common with the larger triangle. And I noticed they share angle C and angle F.
Okay.
So I know that since those two smaller triangles are congruent, that angle C and angle F are going to be congruent. That's because of CPCTC. And again, the reason why I'm picking those two angles is because they have a relationship with the bigger picture. I got to just keep connecting it.
Mm-hmm.
Like, why do I need this? Now the question is, why the heck do I say angle C is congruent to angle F? That doesn't have anything directly related to the isosceles. However, if angle C and angle F are congruent, those are part of the bigger triangle.
So I'm going to redraw this.
Yeah, I like that idea. When I have those two angles congruent, C and F, those are the base angles technically.
Uh-huh.
Which then means the sides across from them are congruent. So I could say segment AC is congruent to segment AF, and that's because of base angle theorem converse.
Right, because here we knew the angles were already congruent, so we're going to use the converse theorem to say the sides are congruent. Again, the base angle theorem proves angles congruent. The converse takes the angles and turns it into the sides then being congruent.
So BAT converse Now, I'm still not done.
Right, because that's not even what I was trying to prove.
I've proven in the bigger triangle, 2 of its sides are congruent, which essentially means it's isosceles. So I can go ahead and say triangle ACF is isosceles, and that's because of the definition of isosceles. Now, while Ms. Hooker is finishing writing that down, something I see a lot of people want to do is jump from step 4 to step 6. The definition doesn't say anything about, if you look it up, it doesn't say 2 congruent angles. It says 2 congruent sides. So you do need to state the sides are congruent before you can say it's isosceles.
And that's just going back to make sure you know your definitions and what they really state.
Exactly. All right, one more. This particular one, notice the picture, got a lot going on.
A lot of triangles.
A lot of triangles. The given's not as lengthy, which I kind of like.
Yeah, how come you got to write the one where the given wasn't so long?
I just planned it. I'm smart.
That's funny.
All right.
I'm looking at this, and I think, let's go ahead and mark. We've got angle KRM, so that little bitty angle there is congruent to angle PRO. And we know another set of segments that are congruent, KR and PR. And our goal here, I am going to look at this one because just looking at this, I've got 2 congruent statements. So I want to know, do I need to prove the triangle's congruent, or what would be helpful on this one? And because right now I'm thinking those little bitty triangles, I might be able to talk about them. I only have 2 pieces, but let's just take a look. I'm trying to talk about RM being congruent to RO. And I noticed that those are also parts of those little bitty triangles. So I'm thinking that maybe if I can prove those little triangles congruent, I could use some CPCTC action to be able to say, hey, those sides are also going to be congruent.
And so those are the 2 triangles she's talking about. The 2 kind of outside there. Okay.
Okay, so they don't give me anything else in my given, just 2 congruent statements.
Which is helpful, but we still need one more.
Right, and I know that when they give me information, they give it to me for a reason. There's not anything when I look at the picture that's like reflexive or anything here. But if I look at that as one larger triangle.
So which triangle are you talking about?
So I'm talking about like triangle KRP. If I look at that as one larger triangle, I then see that it's isosceles because they tell me that KR and PR are congruent. And if the triangle if it's isosceles, those base angles are congruent, which that's going to help me because those base angles are also angles within those smaller triangles. So I'm going to say that angle K is congruent to angle R, and here angle P, sorry, thank you. And as I'm looking at that, okay, I know that I'm proving angles, the base angles congruent, so that's the base angle theorem.
Good. So you guys see that in the larger picture, kind of giving the idea that these are congruent. And then, like, go to the original, that's these guys right here.
Okay, so now I have enough to say that those little triangles on the sides are congruent because I've got a side that's included between 2 angles, so angle, side, angle. So I'm going to say triangle KMR is congruent to triangle POR. And that reason is angle, side, angle. Now, I wanted to prove that RM is congruent to RO, but since I know that those triangles are congruent, those are parts of those triangles. So I'm going to use some CPCTC to say that RM is congruent to RO, and my reason corresponding parts of congruent triangles are congruent.